Hi everyone. Today we are going to move on to chapter 8, where we're going to spend some time looking at specifically acid-base equilibriums. So in this chapter we're going to be looking at how the concept of equilibrium compares strong and weak acids and bases, be able to explain some of the equilibrium expressions such as Kw, Ka, and Kb, and be able to communicate different acid-base equilibriums and systems. All right, so that's going to be the main focus. So before we can start moving forward with the equilibria, we need to do a quick little review and describe what is the nature of an acid and a base. So from your previous science classes, we've classified acids and bases based on their properties. We know that acids are good conductors of electricity. They are clear colorless solutions, and so therefore indicators assist in determining if it is an acid or a base, such as litmus paper, which turns red. Red litmus paper will stay red, and blue litmus paper will turn red in the presence of an acid. They are sour tasting. They react with different metals to form hydrogen gas, corrosive to the skin, and they have various strength depending, and we use pH to help express how strong an acid is, all right, or how weak it is. Likewise, we know that bases too are also good conductors. They are blue in the presence of litmus paper. They're bitter tasting. They feel slippery. They destroy some of the acidic properties, so therefore can help neutralize acids, and we can express the concentration using pOH. Right, so pOH helps us to determine the strength of a base. All right, so we have two different scales that are present here. Now, the first person to come up with a theory to explain the differences between acids and bases was Svante Arrhenius. He was a Swedish chemist, and he performed a series of different experiments and helped to explain his observations of what an acid and what a base was. He found that acids produce hydrogen ions. All right, they're going to produce hydrogen ions, H plus aqueous. And the hydrogen ion is a hydrogen atom without an electron. So therefore, we also call it a proton, all right? While a base produce hydroxide ions, which is OH negative 1, when they are placed in water. So here are some examples. We know that when we place hydrogen chloride into water, it ionizes and forms hydrogen ions and chlorine ions, all right? And we know that HCl, hydrochloric acid, is an acid because of the fact it produces these hydrogen ions. Likewise, sodium hydroxide, all right, when it dissociates in water, when we place it in water, it will break down into sodium ions and our hydroxide ions, and it's the presence of these hydroxide ions which makes it basic. All right, so because it has the ability to produce hydroxide ions, that is the definition of the Arrhenius base. Now the problem here is this theory was limited only for bases that contain hydroxide ions. Okay, as well, we're assuming that all acid and base reactions occur in aqueous solutions, meaning it occurs in water. All right, so those are some two assumptions that we're limiting in the Arrhenius theory. So therefore, another more general explanation of what an acid and a base was developed by a Danish and English chemists, Bronsted and Lowry. Oops, sorry guys, I don't know what happened here. My apologies. Let me get this fixed up. There we go. Press the wrong button here. Okay, so getting back to what a Bronsted-Lowry theory is. So their general theory is very simplified. They define an acid as a hydrogen ion donor and a base is a hydrogen ion acceptor. Based on this general explanation of what an acid and a base is, it helped to explain these two limitations of the Arrhenius theory of an acid and a base. All right, so let's take a look at what's taking place here. In an acidic solution, what normally happens here is if we have hydrogen fluoride and we place it in water, one of these hydrogens is donated to the water molecule. Okay, hence hydrogen, by the definition, hydrogen fluoride therefore is the acid, and therefore water is the base, okay, because it's accepting the hydrogen ion. All right, so what results is the fluoride ion and the hydronium ion. Short form for hydronium ion is the hydrogen ion. Okay, in a basic solution, we can see what's happening. We know that ammonia, NH3, is a weak basic solution. However, there is no hydroxide ions, yet it does behave as a base. So if we look at the definition of the Bronsted-Lowry, notice what happens. When I put this in water, the ammonia into water, one of the hydrogens from water is donated to the ammonia molecule. All right, hence making water the acid, and my ammonia, because it's accepting the proton, is the base. Okay, so therefore it forms ammonium ion and my hydroxide ion. Okay, so this helps to explain why ammonia with water can be an acid-base reaction. So now this leads us to an important definition and explanation of how the Bronsted-Lowry theory explains acids and bases. We call them conjugate acid and base pairs. So since an acid and base reactions are reversible, the hydrogen ion or proton can occur in both the forward as well as the reverse reaction. So therefore the Bronsted-Lowry acid, which is your hydrogen ion donor, and the base are found on either side of the equation, and it helps to solve the issue that water does not have to be the solvent. All right, so let's take a look at some examples. All right, if we take a look here at this hypothetical acid. All right, the hypothetical acid contains HA, A for acid. Here we've got the hydrogen, which is the proton. So what happens is this hydrogen is donated to water. Hence, this is my acid, making this the acceptor, so therefore it's my base. All right, so that represents the forward reaction. Okay, the acid donates the hydrogen ion to the water molecule. Okay, now in the reverse reaction, the hydronium ion, okay, so if we were to do the reverse reaction going in this direction, this too would be my acid because it would donate its hydrogen ion to the A negative anion. Okay, so therefore making this my acid and this my base. Okay, and so therefore we call this the conjugate acid and the conjugate base. I'm putting CONJ for conjugate for short form, and A for acid and B for base. All right, so the conjugate acid is the acid formed when the base accepts a hydrogen ion from an acid. Okay, and likewise that is the conjugate base. So let's look at our hypothetical base situation. So B stands for my base, and what happens here is the water molecule donates the hydrogen. So therefore This is my base because it's accepting the proton, and the water is acting as the donor, so therefore it is the acid. Okay, so this is my acid, this is my base. If for the forward reaction. Now for the reverse reaction, the BH plus, this is what's donating the hydrogen here, so therefore this is my conjugate acid, hence this is my conjugate base. Okay, because it's acting as a base. So this just gives you a pictorial diagram of both situations. So a conjugate acid-base pair are two substances that are going to be related to one another by donating and accepting a single hydrogen ion. Now don't forget, this single hydrogen ion we also call a proton, all right, for short, all right, which is my H plus ion. Okay, that's my hydrogen ion by definition. All right, let's do some examples of identifying and being able to label which ones represent my acid-base pairs. So if we look at the first example, what you need to do is take a look at the forward reaction and see who's accepting and who's donating. So if we see here, the HCl in the react product side has lost the hydrogen. So this hydrogen is being donated. So therefore this is my acid. Therefore the one that's accepting by definition of the Bronsted-Lowry is my base. Okay, over on this side likewise, so this would be then my conjugate acid, because in the reverse reaction it would give up or donate the proton, and hence this one would be accepting it. So therefore this is my conjugate base. Okay, all right, looking at my next example, we're looking to see which one is giving up. Both of them do contain hydrogen, but we see that HCN on the product side has lost it. So therefore this is being donated to the water. So here, this is my acid by definition because it's donating the hydrogen ion. Hence, water is acting as the base because it's accepting that hydrogen ion. Now, looking on my product side, therefore this is my conjugate acid because it will, in the reverse reaction, give up its proton or donate it, and this one will accept it. So therefore this becomes my conjugate base. All right, so hopefully you're getting the idea of what we're doing here. All right, so here are some multivalent acids. So we look to see what's actually taking place here. Here's my hydrogen. It's being donated to the phosphate. So by definition then, HSO4 negative 1 is my acid. This is my base because it's accepting the proton. Likewise on this side, we're going to have this one donating in the reverse. So therefore this would be my conjugate acid. Hence, this is my conjugate base. All right, looking at my last example here. Once again, I look to see which one is donating the hydrogen ion. So this is going to donate a hydrogen ion to the acetate. So therefore this is my acid. This represents my base. This represents my conjugate acid. And so hence, this is my conjugate base. Water is acting as the conjugate base in the reverse reaction. All right, here are a few other types of questions that you may potentially see. It says, what is the conjugate base of HNO3? So by definition, we can determine the conjugate base by removing one hydrogen from the acid. So the conjugate base, therefore, if I take away the hydrogen, would be NO3 negative 1 would represent the conjugate base. Okay, it would represent the conjugate base. Now they tell us that HSO4 minus 1 has a conjugate base. We want to write its formula. So to determine it, we're going to remove the hydrogen. Once again, we're going to take away this hydrogen to come up with the conjugate base. So it becomes SO4. But because we're removing that hydrogen, if you recall from grade 11, we need to change the charge of the ion. Okay? So when we remove a proton or an H+1 ion, we add a -1 charge to the polyatomic ion. This is hydrogen sulfate. Okay, so please remember that from grade 11. Okay, when we were coming up with all of these derivatives. So if I take away this hydrogen ion, which has a charge of +1, I'm going to increase the charge of -1 to -2. Okay, so that's why its charge is really SO4 -2. All right, so this is a tricky one. Okay, you got to remember some of your nomenclature rules from grade 11. Now it says, what is the formula of the conjugate acid of OH -1? So we need to add a hydrogen to this. Okay, so it's going to be OH plus H plus is going to form H2O, all right, which is the conjugate acid. All right, it will represent the conjugate acid. And looking at my last example here, we got PO4, which is the phosphate ion, is a strong bronze telluric base. We want to determine its formula, its conjugate formula. And so we can write a couple different things here. What is the conjugate? If we're adding the hydrogen, if we're just going to add one hydrogen, it would be HPO4 -2. Because I'm adding that extra hydrogen, remember, we have to decrease the charge from -3 to -1. Okay? Or if we want to add additional ones, we can say that it is H3PO4, okay, or H2PO4 -1. Okay, so if I add two of them, it's going to have a charge of -2, but if I add three, it's going to have a charge of -3. So adding one hydrogen ion, 2 or 3 here. All right, so making sure that we write the correct formula. We will use this one here because we will just assume that we're adding one hydrogen ion to the conjugate acid. Okay, that's what we will work towards. All right, one other new concept that we need to look at is called amphoteric substances. These are substances that can be acids or bases depending on what other reactant they are being mixed with. All right, so if we take a look at our example here, we've got HCO3 -2. We see that water is acting as the acid. All right, but in my second example, water is acting as the base. Okay, so water is a good example of an amphoteric substance because it can behave either as a base or either as an acid depending on what reagent it's being involved with. Okay, so water is a very good example here because it can act as an acid and it can act as a base. All right, so here are some other examples. There's an error here. Sorry, it should be properly written here. So if we look to this example, we've got H2O plus HCl. So it's the HCl that's donating the hydrogen ion to the water. So this is my acid, hence this is my base. Okay, now if you look at this second example, what's going on here? One of the hydrogens is donated to the ammonia. Hence, water this time is acting as the acid and ammonia is acting as the base. All right, so very important concept to remember. And lastly, the final thing that's discussed in this section to describe the nature of acids and bases is we're going to introduce the acid ionization constant. And we call this equilibrium constant, Ka, to identify that it is dealing with exclusively with acids. So the reaction of a weak acid with water is going to form a dynamic equilibrium. Okay, and so this again is just the general equation. All right, so this is my general acid being placed in water. Okay, so it donates the hydrogen ion to the water, making HA the acid and my water behaving as the base, and it forms the conjugate base A negative 1, my anion, plus my hydronium ion of H3O plus. Now our equilibrium law equation can be written in the following way. We can go just like we did with every other equilibrium law expression. We are going to place the products over the reactants. But you'll notice that this is not a homogeneous reaction. So therefore, we need to incorporate the water H2O liquid into the equilibrium ionization constant Ka. All right, so I take that out. If we omit water, we include it into the equation. So hence then, my equilibrium law expression here to find Ka then is generally always going to be the anion that results times the hydronium ion that forms over my acid HA in this case. All right, so this represents the general equation. All right, so the acid ionization constants are also tabulated. So you've got a very short list here on the right hand side. It's unique to different acids. And so we're going to see how we can use them in describing and explaining equilibria of acids and bases in the next few lessons. All right, so for today, folks, please read over 8.1 and try the following homework questions. Good luck, and we'll see you in the next lesson.